physician. And Gary is a molecular biologist at Massachusetts General Hospital and a professor of genetics at Harvard Medical School. He's one of the discoverers of gene regulation by microRNAs, and he's also involved in the design of an automated genome sequencer to be used on Mars. Okay, so Gary, maybe we'll start with you. So the idea of panspermia, that primitive life spreads between planets, usually involves asteroids landing and sending biological material into space. The debate about whether life began on our planet has been going for a long time, whether it began that way. What is your personal view?
I don't think there's that much of a debate on whether life evolved on the planet. I think it's sort of the dogma that most biologists would believe from the evidence is that there was an earlier RNA world, and 99% of them would believe that RNA world was here, and that the primordial soup on which chemicals polymerized into membranes and biochemistry and metabolism, and finally into DNA all happened here.
Well, the question was about panspermia, right? So,
right, but so the other side of it would be, oh, it didn't happen here, and life just sort of came to Earth.
Yeah.
And most biologists would say that's a very cowardly view. It's just putting the problem somewhere else, and it is cowardly, but it might be true. And the reason that so I happen to subscribe to that view, but it is a minority view. And the reason I subscribe to it is that if you look in the fossil record at where you first find sort of bacteria-ish things, where the general view is no, bacteria are quite primitive, which is wrong. Bacteria are way better than we are. They've transformed our planet. They've made an oxygen atmosphere. They do planetary science on a planetary scale, more than astronomers and planetary scientists do. But so that they happened, they were found within a few hundred million years of the cooling of the Earth. So that would suggest that you go all the way from raw chemistry to real biology in a very short period of time. So you'd have to say evolution all the way to bacteria is really dead easy, and it's going to happen over and over and over again. Or that, Earth is just a rich medium, and bacteria-ish things came from afar.
So 200 million years is too short of a period of time for you, and a few billion years is good enough. So this is this range. Right,
because it only buys you. If life came from somewhere else, you get 10 billion years or so.
Right. But that's enough time for you to.
Well, I wish it was a factor of 100 and not 10.
Okay.
Sorry. Exactly. I'm against the Big Bang.
Natalie, Natalie, I don't know whether you're familiar with this paper of last week from Edinburgh University. Found that you maybe even don't need meteorites to spread life. The fast-moving particles are enough. What do you think about this?
So panspermia is this idea that life could have originated someplace else and then been spread to another planet. And it can do that either through collisions, lofting material into the air and letting it go on a course through interplanetary space, or as you've mentioned in this other paper, through more recent bombardment by dust in the upper atmosphere. It's seemingly counterintuitive, actually, when we consider this. It sounds kind of crazy, until you stop and realize that planetary formation is a very dynamic process. The early solar system, early epoch of planetary formation, you had planetesimals that were dynamically interacting both with each other and with their nascent disk. So it was a very violent and dynamic process. And that gas and dust clears out rather rapidly, but even today we have this remnant material. So you go through the calculations and you say, yes, it's possible. But I guess I would ask, is it necessary? I agree with Gary's viewpoint that it kind of violates an Occam's razor, if you will. I don't think it's necessary. Moreover, in the solar system, the process takes hundreds of thousands of years. So it's very slow. It's not very efficient. I find this technique much more intriguing on some of these other planetary systems that we found, like the TRAPPIST system, where you have 7 planets packed dynamically into an area that fits within, let's say, Mercury's orbit. So there, the transfer process is like decades, 100 years, not 100,000 years. So I think in systems like that, it's much more compelling.
And can you help me to visualize? So let's say there is asteroid coming in the atmosphere. Obviously, it's very hot. Temperature is very high. And let's say there's some bacteria traveling there. So are they going to survive this last phase?
Well, that's the question, whether you're talking about a collision, which is very violent. So an organism, and we can think about either life, actual microbes, or maybe just organics. If we can take these complex molecules and allow them to survive these violent processes so that they can then seed life someplace else.
How they will survive?
Well, it's challenging. They're going to have to burrow themselves into the lithosphere of an object. They're going to have to survive.
So they should be a little bit underground, right?
Yes, that's right. And during their interplanetary voyage, they probably also have to be buried within the rock and then released rather gently as they collide back on the other planetary surface. So, the odds of that happening are small. It's difficult, but calculations say that it's possible. I'm convinced that it's possible, and that these events happen frequently enough during the formation stages and even later stages of a solar system's life that it's possible, but hard.
So, Gary, do you agree that you kind of need to sit inside this rock and hide there for a while and then survive the landing?
An asteroid smallish, a few meters across coming towards Earth is at 80 degrees Kelvin. Enters the Earth's atmosphere, yes, it gets very hot, where the crust smalls off. The center is still 80 degrees Kelvin, right? Now, when it collides, there's a lot of energy release, but there's shock waves where there isn't heating, and Jay Mellish has done lots of calculations, even experiments on this. So transfer of life by meteoritic exchange it's hard, but it's not impossible. The other thing to keep in mind is that this revolution in exoplanets that you've been so involved with, it's been magnificent. It has all these hot Jupiters that are spewing planets like crazy. So the movement between star systems can be entire planets. It doesn't have to be pieces of rock. If Earth got ejected tomorrow, we wouldn't do too well, but the bacteria on Earth would do just fine, thank you very much. And for a billion years to sort of hang out, they could do that.
Meaning that the Earth could be older than 5 billion years. So in that case, the Earth would be older than 5 billion
structure, but it's something analogous to Earth. Could see
Something like that.
Yeah, it could go to the next planetary system. And every star has an orbit belt around it probably, and those orbit belts are very loosely coupled and exchanging like crazy as the stars sort of sweep next to each other.
Lyman, to sort of put some boundaries on how early in the life of the universe life would have emerged. We know that the universe is roughly 15 billion years old, 14 billion years old rather, 13.8. So at what period of time we can assume that now life can emerge?
So something like the first stars have to form to make these elements of life. So something like 1 million years, the process could start. And just we heard about earlier, early on is also a great time because you don't have to travel these great distances. Things are closer together.